All right. So I want to thank the Summer Science Program and Meg in particular for inviting me. It is definitely a pleasure to be here to talk about this, and I really want to thank all of you, especially the high school students who are choosing to spend this beautiful afternoon hearing some clown talk about some weird particle called the Higgs Boson. And it's an unusual talk because my main goal, more than anything else in the talk, is that an hour from now you can leave this auditorium and be able to answer the question, what was that talk about? Usually you kind of expect that as background before you give a talk. As Meg mentioned, this is a big, big event. It was in the news a few weeks ago. Some of you, if you read the science section of the news, may have seen this announcement that Higgs Boson has been discovered at the LHC, this big particle accelerator at CERN, this research institute in Switzerland, and it has generated the level of excitement among particle physicists that the media usually reserves if Justin Bieber changes his hair color or something. This has been a huge deal to the kinds of people who get excited about new particles. And so my goal in this talk is to explain to you what was actually discovered and why it's considered so important and what it means for our understanding of the universe. And so really, well, the Higgs boson, it's a particle. A lot of what this talk is going to be about is this field of particle physics. And at a basic level, I can say very simply what that is. The goal of particle physics is to answer the question, what is everything made of? And so by the end of this talk, I hope that you will understand how this new discovery fits into that long-term project of trying to understand, if you look at all this stuff around you, at the smallest, most basic level, what is it made of? So here's a rough outline. I said that the Higgs boson is a new particle, so I'm going to be talking about the field of particle physics, and I'm going to start by giving you a little bit of background. The one PowerPoint slide summary of particle physics from approximately 500 BC to the early 1970s. And it will set some context. Where have we been in thinking about this question of what stuff is made of? What kinds of answers have we been thinking of? So you have some idea of how these new discoveries fit into that. And then I'm going to talk for a while about this one particular theory, the Standard Model of Particle Physics, developed in the early 1970s. And that is still today our current best understanding of what the universe is made of. And I will try and describe what that theory says, what we think the universe is made of, and then how the Higgs boson fits into it. And then, finally, I'll actually get to talking about the Higgs. And when I do that, I want to talk about two things. When you refer to the Higgs, it refers to two different but related things. And this is part of what makes it so confusing to read news articles about it, is that almost nobody makes a clear distinction between these two things. They're closely related, but they're not the same. And as you read the news articles, it can get very confusing for that reason. One of them is this thing called the Higgs field, and I'll explain what that means. If you've seen newspaper articles saying that the Higgs is what causes everything to have mass, that's all about the Higgs field, and I'll explain what I mean by that. But that's not actually the thing they found in Switzerland. The thing they found in Switzerland is this thing called a Higgs particle, or a Higgs boson. And I will try and explain how those two are related, and then get to this very basic question, why is it so important? And then finally, I'll wrap up by saying some of the open questions, what you should look for coming out of new particle physics discoveries in the next 10 to 20 years or so. So, going back a little bit, I said particle physics is the attempt to understand what everything around us is made of. Well, you look at all the stuff around us, there's trees and clouds and rocks and dirt, and I could go on virtually forever. It seems to be made of an almost infinite number of things. And every culture has grappled with this question. If you look closer and closer, what are all those different things made of at root? What are the building blocks? And among those, many of the ancient Greek philosophers addressed this question, and they had two particular ideas that are relevant to the way we understand the world today. One of which is that all of these different things are composed of a small number of basic elements combined in different ways. The difference between rubber and wood and milk is just what proportions of these four basic things, earth, air, fire, and water, that they have in them. And that idea is original to a man named Empedocles, and I feel obliged to mention that, not because you should remember the name Empedocles, but because everyone who talks about this says that it was originated by Aristotle. And so I feel obliged to correct that. Aristotle borrowed the idea from someone who had it centuries before him. And as far as we know, Plato was actually the first person who coined the term element to refer to this idea of one kind of substance, a variety of substance out of which everything else is made in different mixtures. The fact that they chose these four, earth, air, fire, and water, not particularly relevant to the way we understand the world today. But the basic idea very much is. And one other idea that we got from the Greeks that has really influenced the way we think about particle physics today is that if you divide things further and further and further, you come to ultimate fundamental building blocks. And this idea, so far as we know, is original to a man named Democritus, another ancient Greek philosopher. And he coined the term atom, which comes from the Greek word for indivisible. So if you take a rock and you split it in half, you have a smaller rock. And you split that in half, you have an even smaller rock. And you keep going and going and going. Eventually, you get to something you can't split in half anymore. Those are the atoms that everything is made of. And that, too, is part of how particle physics sees the world today. That everything is made of these fundamental building blocks, which we would now call particles. And so, the quest of particle physics is to figure out what are the properties of the particles that everything in the universe is made out of. So that's ancient Greece. And now we can jump forward to more modern times, the last few centuries, when people started investigating the things that we now think of the universe as being made of. The elements now were things like hydrogen, oxygen, carbon, nitrogen, and so on. And people were able to do measurements and figure out, yeah, stuff like water and wood is made of different mixtures of these basic elements. And all the objects, all the matter around us is composed out of this relatively small number of elements. And then people realized that these different elements are made of these small, hard objects. So they borrowed Democritus' term, atoms. And that what makes one element different from another is that they are made of different types of atoms. There is a nitrogen atom and an oxygen atom. And when you put a bunch of nitrogen atoms together, you get nitrogen. And all the other more complicated stuff like water is just some number of hydrogen atoms, some number of oxygen atoms, and so on, mixed together in different ways. So that was a pretty good picture. A little bit complicated. There are several hundred of these elements, and people kept discovering more and more. So it's not quite the nice, simple idea that Empedocles or Aristotle had of the world. Four things, and that's all there is. But still, it has a certain order to it. And that was pretty much the situation going on towards the end of the 19th century. And at the very end of the 19th century, you have a crucial discovery that paved the way for a complete change in our understanding of this question. A man named J.J. Thomson found a particle that we now know is part of what makes up an atom. A particle that we now call an electron. So, in the early 20th century, the question was not what elements are things made of, and what are the properties of the atoms that make up those elements, but what are those atoms made of? And in the first few decades of the 20th century, that question was answered. I already mentioned Thomson. A man named Ernst Rutherford discovered another particle called the proton. And between them, they got this nice picture of what an atom is. It's a dense nucleus of protons with electrons spinning around them. And all of the different elements, all the different kinds of atoms, are just different numbers of these particles. A certain number of protons and electrons gives you a nitrogen atom. Different number gives you an oxygen atom, and so on. So now, we've gone from hundreds and hundreds of elements that make up, of building blocks that make up all of matter, to 2. And then another crucial discovery was made by a guy you may have heard of. This guy named Albert Einstein came up with an idea. And obviously you've heard of Albert Einstein, and presumably you all know that he created the theory of relativity. What you may not know about him is that he never got a Nobel Prize for that discovery. He actually got the Nobel Prize in physics for this idea. He said that in addition to matter being made of these fundamental particles, light, radiation, is also made of individual particles, which we now call photons. And so now we have this beautiful picture of everything the universe is made of. We've answered particle physics. And that was the situation in about 1930. Matter is made of protons and electrons. And the radiation that passes between objects is made of photons. It's a nice, simple, elegant description of everything in the universe, just what the field of particle physics is all about. It was doomed almost from the moment it came into existence. Because what happened is people started discovering lots more particles that weren't made of protons or electrons or photons. I mentioned that in 1930 they pretty well had this model in hand. Just 2 years later, a man named Chadwick discovered actually the nucleus, the center of the atom, is made of 2 kinds of particles. It's protons and this other thing called neutrons. In the same year, people found this new kind of particle, which we now call antimatter. Every kind of particle we know about, there's a corresponding antiparticle. So for the electron, there's an anti-electron we call a positron. And it has some of the same properties and some different ones, and if an electron and a positron meet, they annihilate in a burst of energy. Things are just starting to get more complicated. And this just kept going on and on and on. People found things that we now call muons and pions and kaons and lambda. And I could go on for hours. The early to mid 20th century was just this huge explosion of new particles. One of the most famous physicists of the 20th century was a man named Enrico Fermi, who once commented that if he'd known he was going to have to memorize all these particle names, he'd have gone into biology instead. Just to give you some sense of this, I've copied a very, very short partial list of some of the particles that people were discovering along with their associated properties. And it was utter chaos. There was no pattern that people could find. They were just getting a longer and longer list, and for each one they measure and tabulate its properties. Something was wrong. And everyone in particle physics agreed the fact that it was getting so convoluted and so arbitrary meant there was something we didn't understand about it. And based on previous experience, the best guess was maybe these aren't really the fundamental particles. Maybe we're making the same mistake that people made about the elements. Maybe these are really made of a small number of simple particles combining in different ways. And that ultimately led to the standard model of particle physics. I can't tell you, here's the person who invented the standard model. I can't even tell you, here's when it was invented. It was a long process. Gradually, pieces of the puzzle over several decades were put together by many different people in many different ways. People explained, oh, this group of particles, you can explain that in terms of this simpler set. Oh, and these two things that seem very different, that's actually the same kinds of particles acting slightly differently. Slowly, all the pieces came into place. And in the early 1970s, I put on the first slide the date 1974, somewhat arbitrarily. That's about when it all came together. We got this picture of particle physics that is the one we still have today. It's not quite a thing of great beauty, just drawn like that. But it's a whole lot better than that chart I had on the last slide. And unlike that random chart of properties all over the place, there's a regularity to it, in much the same way that there is a periodic table. It consists of 17 particles. People count it in different ways. But I'm going to call it 17. And I grouped them into several different categories. People group them into several different categories. And I'm not going to go into detail about them, but I'll say a few words. First off, you may notice, if you look around this chart, you can't find proton or neutron anywhere on there. We don't believe that's fundamental anymore. We now believe that protons and neutrons are made up of these kinds of particles called quarks. And in general, they make up all the particles that act kind of like those nuclear particles, the things in the nucleus. Electron, by contrast, is still in the list. To this day, particle physicists believe that an electron is a fundamental building block of the universe. It is not made of anything else. It is one of the ultimate particles that everything else is made of. And, turns out, it's part of a group of 6 particles that have many of the same properties. We call leptons. And I could give a whole talk about what that word means and what those properties are, but it's not the topic of this talk. And then there's the good old photon, radiation. And people discovered that there are other kinds of radiation made of other fundamental particles that are similar in many ways to the photon, but have slightly different properties. And then there's this last category, the Higgs boson. And I'm not going to really talk about that at all right now, because I'm going to spend the entire second half of the talk talking about that. So the only thing I'm going to say about that at the moment is that it is extremely different from everything else in this group. The theory consists of 16 particles that are in many ways kind of similar to each other, and then this one that behaves very differently from anything that had been observed to that point. And, not to leave you in suspense, I know by now some of you are wondering why I chose to color approximately half of these particles green and the other half gray. And the answer is, everything in green is a particle that, at the beginning of 1974, had been observed. Everything in gray had not. And that's a crucial point. Because what it means is that in addition to explaining all this stuff we'd already seen, this theory predicted a lot of new things that we should see if we go out and look for them. And what has happened over the last 40 years is people have done careful searches. The Standard Model predicted, go out and look for a particle with these properties and you'll find it. Go out and look for a particle with these properties, it'll be there. And one by one, they've all been discovered. In the 1970s, you got the charm, the tau, the bottom, the gluon. Into the 80s, the W and the Z. In 1995, the top quark. And then ushering in the new millennium, the tau neutrino was discovered in the year 2000. All of these with precisely the properties that the Standard Model said they should have. It's been a huge success. And there has not been one experiment in those 40 years that didn't come out the way the Standard Model predicted. Everything that it said should be there has been found now, except for this lonely little thing. So summing up the Standard Model, it is a theory that correctly explains every subatomic event that humans have ever witnessed. Every particle experiment, every laboratory experiment done in human history, we can account for the results using the Standard Model of particle physics. And it includes these 17 particles and all of their properties. It doesn't just say, you'll find those particles. It says, if you bang this kind of particle and this kind of particle together with this much energy at this angle, here's exactly what you should expect to see coming out. And thousands and thousands of experiments have been done, and it always has worked, without fail. And, as I mentioned before, that includes that half the particles in the model were discovered not as part of making the model, but because of the model, as a prediction of the model. Except that one. This is a picture of Peter Higgs. He is one of several people who independently came up with the idea that led to the Higgs boson, the theory of the Higgs boson. He has commented himself that he doesn't think it should be called the Higgs boson because he was one of a number of people that, working independently at about the same time, came up with this idea. But history seems to have made its judgment, and everyone refers to it as the Higgs boson and the Higgs mechanism. And so I will simply follow that practice, and you can keep in the back of your mind that really he shares the credit with a number of other people. And that's the one piece that, since 2000, has still been missing from our verification of the Standard Model. But really, is that such a big deal? 17 particles. We found 16 of them. Sure, it's nice. You want to find the 17th. It gives you a sense of closure. It's annoying to have a box with 16 green boxes in it and one gray. But that's not worth billions of dollars, necessarily. So what I want to spend the second half of this talk doing is explaining to you why the Higgs, in particular, is very different from all the other particles in the Standard Model, and tells us something dramatic and surprising about what the universe is made of. So to answer that question, what's so important about the Higgs? What does it do in the Standard Model? The easiest way to do it is to say, let's imagine a universe without the Higgs. What if we had just made a Standard Model with 16 particles? All the ones we have, with all their same properties and everything that we tried to put in, except the Higgs. And in essence, that's what people did. Throughout the 1950s and 60s, they didn't call it the Standard Model, they hadn't put all the pieces together. But at first, they were developing these theories, and they didn't have a Higgs in them. And they found they worked great. They could explain all these different aspects of the universe, all these different particle interactions they were seeing. You could explain with these different theories that people were coming up with, the quarks and the leptons and so on, except for one. There was one prediction of these models that didn't quite match observation. They unequivocally, unambiguously predict that every single particle in the universe should have zero mass. That is something of a conflict with observed behavior. The particles we see around us, for the most part, have mass, with one exception. Or there's one exception that was known early on, the photon. Light doesn't have mass. So you can credit these pre-Higgs theories with getting that one prediction right. But all the other particles, they said, should also be massless and should behave more or less like the photon. That's a problem. And to explain in more detail exactly what the problem is and how Higgs figured out how to fix it, I have to step back and ask a seemingly silly question. How do we know that the particles around us have mass? What's the difference in behavior between a particle with mass and a particle without mass, an electron and a photon? There are, as you might guess, a lot of answers to that question. They behave differently in many ways, but there's one that is the clearest, easiest, and simplest difference that right away tells you, does a particle have mass or not? Photons, because they are massless, move through space at exactly the speed of light. 3 times 10 to the 8 meters per second. Always. Every photon moving through outer space right now is moving at precisely the same speed, which we therefore call the speed of light. I could not invent a constant of nature that represents the speed of keys, because they can move at any darn speed they feel like. Now they're at rest. Now they're moving slowly. Now they're moving kind of quickly. That's how massive particles behave. You can make them go faster or slower. You can make them go any speed whatsoever, as long as it's less than the speed of light. Photons can't do that. They can't speed up. They can't slow down. A photon moving through space always moves at the speed of light. So there's your clearest difference between particles with mass and particles without mass. And so one way of framing this problem I mentioned is that the standard model without the Higgs predicts that every particle in the universe should be moving at exactly the speed of light all the time. That would be a problem. But there's a caveat to that. You take a massless particle like a photon, and you may notice I kept saying it always moves at the speed of light in empty space. The photons in outer space are all moving at the same speed. It turns out photons moving in matter don't do that. What do I mean moving in matter? If a photon hits that wall, it just stops. It can't move through the wall. But it can move through air, or water, or glass. And when it does move through any of those things, it slows down. If you shine a beam of light at an obstacle, say that's a big piece of glass, or a pool of water, or whatever, you'll find that the photons, as they enter the matter, lag behind. They move at less than the speed of light. Moreover, it turns out, I mentioned there are other differences between the way massive and massless particles behave. Every one of them changes. In every measurable way, a photon moving through matter behaves like a particle with mass. To see why that is, let me give you an analogy. Many of you, I'm sure, can bike pretty fast. Oddly enough, for having nothing to do with this talk, we were just talking about that in the car on the way here. And, you know, good cyclists can get up to 30, 40, maybe even 50 miles per hour. But I challenge you to try that on the bottom of a pool. You can bike on the bottom of a pool. People do it. Not all of them. But they do. But you can't go very fast. And the reason is very simple. The water is literally in your way. As you are biking through the water is made of molecules, atoms, and you keep banging into them. And as you bang into all the molecules in your way, they slow you down. The same thing happens to a photon, a beam of light moving through glass. It keeps banging into those protons and electrons, and they knock it this way and that, and it moves more slowly. So that when it's inside matter, it acts like a massive particle. Okay, hopefully that kind of makes sense, but you may have lost the thread a little bit. Wasn't I supposed to be talking about the Higgs boson? Where'd that go? Well, remember, we were talking about this problem that in the standard model without the Higgs, all particles should be massless. This behavior that a massless particle moving through matter acts like a massive particle is the key to how you solve that problem. So here is the solution proposed by Peter Higgs and others. Maybe there's no such thing as empty space. Maybe what we call empty space is all filled with a field, kind of like a fluid, filling all of space. In between the planets, between the stars, between the galaxies, everywhere. So the Standard Model, without the Higgs, that prediction was correct. Every particle in the universe is massless. But we never see it moving through empty space. We see it moving through this Higgs field that's filling all of space. And just like a photon moving through glass, the electrons get slowed down. That's why they don't move at the speed of light. People often, in stories about the Higgs, use the analogy of stuff moving through molasses. It's a bit overstated, but the basic point is it's moving through something that it interacts with that slows it down, and that's why all of these particles, all of which are intrinsically massless, appear massive to us, because they're moving through this Higgs field that's surrounding us everywhere. Well, if that's true, then that Higgs field has to be completely uniform. If there was a really dense Higgs field here and not much Higgs field here, then electrons would appear to have a lot of mass here and a really light mass here. We never see that. We can observe galaxies billions of light years away in every direction. And we can measure chemical reactions happening in distant stars and galaxies, and they all behave just like the ones we measure on Earth. That wouldn't be true if electrons and these other particles had different masses out there. It would affect those chemical reactions. So we can say that the Higgs field is uniform throughout the entire observable universe. We can also see light from galaxies that has been traveling to us for billions of years. And we can use that to observe chemical reactions that were happening billions of years ago. And they behave just like the ones we see today. So once again, we can say that wouldn't be true if the Higgs field had been different a billion years ago. The Higgs field has to be the same throughout all the space we can observe, and it has to have been exactly the same since the early moments after the Big Bang. And all you have to do is posit that, and you solve this problem. But that's kind of a lot. You could be forgiven for thinking that that's an extreme reaction to the problem. That's not how science normally works. If you have a theory and it makes a wrong prediction, you go back and you tweak the theory. You say, well, let me try changing that parameter there. Yeah, let me add one more particle in here. Maybe that'll fix it. You don't generally say, oh, well, I got this one wrong prediction. Maybe if all of space for all of time was filled with this invisible field that nobody's ever observed, that would fix it. I can answer that in two ways. First, and most obviously, people tried. For decades, people tried to come up with any simpler mechanism that could explain why particles have mass. And they couldn't do it. No matter what they did to the theories, if they didn't put in something like the Higgs field, the theories always predicted that the particles should be massless. But okay, key phrase in there is anything that someone has come up with. That could feel like an imagination on our part. There's no proof that there isn't some much simpler theory out there that explains why all these particles have mass without resorting to this invisible field. And ultimately, it gets at what is science about. You don't believe a theory, whether it's simple or complicated, elegant or ugly, whatever, until you use it to make a bunch of predictions. And then you go out and you test them. And you do that over and over and over again. And once your theory has predicted enough things that match your observations, you start to have a little more confidence. So what we've got to do, if we want to use this explanation, the Higgs mechanism, the Higgs field, to explain particles' masses, You have to measure the Higgs field. So how do you do that? That's a bit of a poser. Because you can't measure something that is completely uniform. To explain why that is, let me give you a simple question you may never have thought about before. How do you know that there's such a thing as air? I know, that's obvious. It's all around us, right? It's not obvious to me. I don't see it. I see walls. I see chairs. I see you. I don't see any air between me and that wall. But I can tell you an experiment that you can try at home with affordable materials to demonstrate that there is this weird invisible field around us called air. It goes like this. The way I knew that there was air when I did that is that I made some of it move. And suddenly it wasn't uniform anymore. There was a little bit more air bunched up here than here. And the air here had a big velocity, and the air here didn't. Once you make something different from one place to another, you can observe it. So that's what people knew all along we have to do with the Higgs field. To use technical scientific terminology, we've got to make the Higgs field wiggle. So this is the mathematical portion of the talk. Bear with me. And when I say mathematical, I mean I've drawn a plot. And this is a plot of the Higgs field. And if you've seen a plot before, hopefully I can convince you in a minute or two that this really does capture the main features that I described of the Higgs field. The height on this plot represents the Higgs field at each point. And you'll notice two salient features. First, it's completely uniform. The height is exactly the same everywhere throughout the plot. And second, it's not zero. It's up here instead. Those are the two features I said the Higgs field need to have. All of space is filled with this uniform value of the Higgs field, and that by itself is the thing that gives particles mass in the theories. But that's not the thing they observed in Switzerland. You can't observe that. Here is the thing that everybody's been looking for the last 40 years. You got to make it wiggle. You got to somehow kick the Higgs field so that in one little place, for one brief moment, its value is different than it is in the other places around it. Well, what do you call that when there's one point in space that suddenly has completely different properties from all the other points around it? You call that a particle. That's what it looks like to us. If you make the Higgs field wiggle like that, we're not going to see a wiggle. It's not going to look like a plot. It's going to look like an electron or a quark or a lepton. It's going to look like there's this one point in space. There's a lot of energy and certain properties that are different from everywhere else in space. That's what a particle looks like. That's what people mean when they talk about measuring a Higgs particle. A Higgs particle or a Higgs boson is a little place where the Higgs field momentarily changes and is different from what it normally is throughout all of space and time. Well, how do you do that? How do you get the Higgs field to wiggle? And the answer is, it takes a lot of energy. You have to pack a huge amount of energy into a tiny, tiny little space and hope that that kind of kicks the Higgs field and makes it wiggle for a moment. Well, we know just how to do that. You take particles, you get them going really fast, so they have a lot of energy, and you bang them into each other. Much of the progress in particle physics in the last 100 years has come from building bigger and bigger machines that can bang stuff into each other harder and harder. And the LHC is the biggest, most powerful banging stuff into each other machine ever made. And what it bangs into each other are protons. So you take two protons and you send them in so they collide, packing all their energy into a tiny space, and it makes the Higgs field wiggle in that spot. And the Standard Model predicts just how much energy, within a range, we weren't exactly sure, but predicts more or less how much energy you need in order to make that happen. And we knew the LHC had it. If the Standard Model was right, the LHC should be able to excite these wiggles of the Higgs field. Problem is, you can't see them because they happen too fast. You kick it like that, the Higgs field will wiggle and settle down in such a tiny fraction of a second that the fastest electronics in the world would not be able to observe it. But what happens when it stops wiggling is it still has all that energy. And that energy goes to creating a huge shower of particles that come flying out from the Higgs in all directions. So here's the plan for the LHC when it was made. You send in two protons, they smash into each other, that makes the Higgs field wiggle, and when it settles down, it sends new other particles flying out in all directions. And you measure those, and you say, hey, there's a shower of particles coming out in all directions from that point that has just the distribution, just the properties that we'd expect from the decay of a wiggling spot in the Higgs field. That is the discovery that was announced a couple weeks ago. So summing up this part of the talk, what is the Higgs? There's the Higgs field, this uniform field, kind of like a fluid that fills all of space throughout all of time. And all the particles in the universe are intrinsically massless, but when they move through that Higgs field, they slow down and they act like massive particles. And that's why we observe a mass for electrons and quarks and leptons. Sort of forgot I had the remote clicker. I don't need to stand there anymore. A Higgs particle is a small place where you make the Higgs field change for a moment. And that's the only thing we can directly observe about the Higgs field. And it takes so much energy that in 40 years, nobody could do it. Until now. Now we have found the Higgs particle. It behaved just like the Standard Model predicted. And our chart looks like that. So much more satisfying. Difference, obviously. Applause for the scientists that done. Now this box is in green like all the others. Hooray! All right, but I still haven't really addressed that question. We already thought we knew that that was going to happen. So when they built the LHC, Standard Model predicted this, and now we've got this nice sense of closure. And I don't want to understate that. That is important. We had to find out. We couldn't really believe that the model was correct until we actually measured that last prediction. And now every particle in the Standard Model has been observed. That's a huge, huge triumph in and of itself. But it is still entirely possible that this could turn out to be the most boring discovery ever made in the history of particle physics. Because it's exactly what we expected. Before the LHC was built, many, many people talked about the fact that the worst possible outcome would be if the LHC found a Higgs boson with exactly the properties predicted by the Standard Model and nothing else. And then we would just say, oh, guess we were right. Glad we spent those billions of dollars. There are other possibilities. First off, it could have not found the Higgs boson, and that would actually have been very exciting in a different way. If it had ruled out the Higgs boson, we would know for sure the Standard Model was wrong, because it had enough energy that the Standard Model said it should excite those wiggles. And then we'd have to go looking for a whole new mechanism. Or, having found the Higgs boson, it could now go on and find that it has properties very different from what the Standard Model says. We don't know yet. It's going to take years to really work out its properties. Or it could find that the Higgs boson is there with all the properties we expected, but then it suddenly discovers some other new particles. There are a lot of possibilities, and we really still don't know. We're waiting to see everything that comes out of the LHC. But it has raised the question, and you can find this question around in the media: are we at the end of physics? Have we figured out the answer to the question, what is the universe made of? And before giving you my answer to that, which I will spoil in advance by saying it's predictable, I will sound a cautionary note. I put up these quotations of a number of very, very prominent high-level physicists predicting the end of physics at different times. And I chose the end of the 19th century. I could have found quotations from earlier, I could have found quotations from later, but this is a whole set of them, because at the end of the 19th century, this was a big issue. A lot of people were talking about whether we basically answered all the questions about how the universe works. And in particular, I like this sequence because going up to 1900, Lord Kelvin, certainly one of the great physicists of the late 19th century, was saying that we're basically done in the same year that Max Planck began developing the theory that later turned into quantum mechanics and showed that everything we understood about physics up till then was completely wrong. This has happened numerous times throughout history. No, we're not at the end of physics. Not only does history suggest that you're usually wrong when you think that's happening, there are also a lot of clear indications of things that we don't know the answers to. Why are there these particular particles with these particular properties? The Standard Model doesn't explain that at all. What it does is it says, if you have these 17 particles with these properties that we've written down and these kinds of interactions and so on, then it matches observation. That's great. That's incredibly important. But it's the same position we were in with the periodic table, with that plethora of particles in the early 20th century. Almost every particle physicist assumes that there has to be some simpler underlying theory that explains why then the universe around us is made up of that particular set of particles. And we know in particular, sorry, got ahead of myself there. There may be other particles. The fact that we discovered these 17 and they explain everything we've seen is not in any way evidence that there aren't others out there that we haven't discovered, haven't seen any evidence for yet. We won't know until we keep looking, see if we find them. And in particular, we actually do know that there are other particles out there that are not part of the Standard Model. I did something weaselly before. I said that the Standard Model explains every subatomic event we've ever measured. That's true. But we've made a lot of measurements of things on much larger scales that you can't explain in the Standard Model. And in particular, in astronomy, we found evidence for at least two other kinds of fundamental objects called dark matter and dark energy. And let me warn you now, these are terrible names because everyone confuses them. They're two completely different things. If you ever be reading about them, we know they're both out there. Dark matter is some mysterious kind of particle that is inside every galaxy, and we need it to explain the way stars rotate in those galaxies. We know it's there, and we've ruled out every particle in the Standard Model. It can't be any of those. So we know there's some other kind of particle out there that's changing the way galaxies behave. Dark energy is a mysterious field Kind of like what I was saying about the Higgs field. It fills all of space. It's causing the universe to expand faster and faster, but it's not the Higgs field. It has different properties. We have no clue what either one of these is, but we know they're out there. There must be some physics beyond the Standard Model that explains these. Standard Model also is completely silent on the force of gravity. Standard Model includes 3 of the 4 forces of nature that we know about. The electric and magnetic forces, the nuclear forces. All of those are included in the interactions between the particles in the Standard Model, and we can explain them beautifully that way. We know gravity's out there, but it's not part of the Standard Model. All right? We should add it to the Standard Model, right? We added all the other forces. Why don't we put in a new part of the theory that explains gravity, just the way we did with the others? People have tried for about 100 years. It doesn't work. Our basic understanding of gravity and our basic understanding of particle physics are completely contradictory. You try and put the two together and you get contradictory results. Nobody knows of a self-consistent way to explain gravity and the Standard Model together. But there has to be one. We also have huge gaps in our understanding of the history of the universe. We know for sure that the universe as we know it came into existence about 14 billion years ago in this event that we call the Big Bang. What was that event? What actually happened? Was it the beginning of the universe, or did the universe just change from being like something else to being like this? Was it a unique event, or do Big Bangs happen all the time in different places? We have no clue. We have no idea what the Big Bang was about, where our universe came from. And all of these are very uncontroversial, in the sense that if you ask any physicist, I think I can confidently say they would agree that these are huge, outstanding questions that we need to solve in physics. The next one, in the spirit of full disclosure, I'd say introduces my biases more. Many physicists would not include it on this list. I consider it of equal importance and equally unsolved with the others. We can write a physical theory that explains how a machine can walk and talk and give physics lectures. We cannot write a physical theory that explains the nature of my subjective experience. Why does red appear the way it does to me? Why does it feel a certain way when I'm sad? Not just why do I act sad, why does it feel that way? In my opinion, that is a huge, outstanding question that science needs to attempt to address. And not really co-equal with all these others, but I did feel obliged to include on the list. That bothers me. And somehow science has to work with it. So, bottom line, we are not at the end of physics. But we are at the end of this talk. Thank you very much. So, I'd be happy to take any questions. Yeah. Excellent. I had on the slide when I originally wrote this talk a little bullet point. I'm going to repeat the question. The question was, why doesn't Higgs field make photons massive? And I had a bullet point that said, why doesn't Higgs field give photons mass? And I said, it's going to be a distraction there. I'm going to wait and see if someone is on the ball enough to ask that in the question. So you just made me.
What's it feel like?
Maybe it feels the same as when you do. I don't know. The answer is because photons do not interact at all with the Higgs field. So the air, I said if a photon hits that wall, it can't go through it at all. If a photon hits some shaded glass, some of it gets through, but a lot of it gets blocked. Photon hits air, it goes through almost completely unimpeded, and it keeps moving at almost the speed of light. Air interacts very, very weakly with photons. The Higgs field interacts relatively strongly with electrons and quarks. It doesn't interact at all with photons. They simply pass through each other unaffected. Every particle in the Standard Model has a different interaction with the Higgs. And that's why some particles are heavier than others. The top quark, when we measured it, we said was really, really heavy. What we actually meant by that is the top quark interacts a lot with the Higgs field, and so it's really hard for a top quark to get through that Higgs field. An electron interacts less, a photon, not at all. And so it remains massless. It doesn't see that there's a Higgs field there at all. Yeah?
Does this mean there's not nothing in outer space?
Correct. The question was, does this mean that outer space is not made of nothing? And that is absolutely true. That's true in other ways, too. First off, there's no such thing as a perfect vacuum. Even in intergalactic space, there are still some electrons floating around. But also, quantum mechanics tells us that even if you take out all the particles, there's all kinds of active stuff happening because there's randomness in quantum mechanics. So you can say, I expect there to be no particles there, but randomly sometimes there are. And that's actually a measurable effect, oddly enough. But this is a third way in which space is not made of nothing. Space is filled with a Higgs field. If you could create a space with zero Higgs, then all the particles in the Standard Model would move through that space at the speed of light. But it turns out that's unstable. If you create a space like that, within a fraction of a second, it will settle back down to a large value Higgs field. So you could, in principle, maybe that's what things were like in the moments after the Big Bang. And actually, there are reasons to believe that's probably true. But within a tiny fraction of a second after Big Bang, all of space got filled with this Higgs field. So there's no place in the observable universe where there's nothing. Yeah?
How come things have mass even though they are not moving against the Higgs field?
Ah, excellent. So what if you have a particle just sitting at rest? Why does the Higgs field still affect it? And I can answer that in a few ways, but the ultimate answer to that is related to the theory of quantum mechanics. None of what I'm describing here works in the same way if you just picture particles as little hard balls. But quantum mechanically, there's no such thing as a particle sitting completely at rest. Every particle has some random motion about where it is. It has some spread. You can't even say it's right here. You can say, well, it's mostly here. But there's a certain chance that it's over here. And maybe it's here. And it's kind of all of them at the same time. And I could give a whole lecture about what that means. I have. But what it means for this is that even a particle at rest in empty space is affected by the stuff around it because it's really spread out in some region of space and moving in some region of space. And the Higgs field fills that whole space. Yeah?
So if you say that things are inherently massless, so they appear to have mass, what
Yes.
do you mean by mass in that context? Like, how do we know that they appear to have mass?
Well, so what I mean is their behavior is the same as what we expected for massive particles. So, for example, they move slower than the speed of light. Just like photons in glass move slower than the speed of light, like massive particles should, but massless ones shouldn't. Electrons, everywhere in the observable universe, move slower than the speed of light. There are other properties. For example, the original meaning of mass, when Newton first talked about mass, what he meant by it is, how hard is it to move something? So, if I take my set of keys, and I want to get them moving, it's pretty easy. Toss them up in the air, because they have very little mass. But if I wanted to take say, this chair, and do the same thing, it takes a lot more force to get it moving. Conversely, if I apply the same force, it moves much less. That's one of the key defining properties of mass. So what I really mean is an electron surrounded by Higgs field is hard to move. And you can think again of the analogy of cycling underwater. It feels like your bike is a lot heavier because it's just harder to get it moving. Yeah, in the back.
So, because you have to use so much energy to make the Higgs field wiggle, does the Higgs field have a lot of mass or does it have any mass?
Ah, excellent. So the question was, does the Higgs field itself have a mass? Is it big or is it small? And I'm going to alter your question slightly before I answer it. Because when you talk about the mass of a Higgs field, what you really mean is the mass of a Higgs particle. The field is something spread throughout all of space. I can't talk about what is the mass of the whole Higgs field, but I can talk about what is the mass of a Higgs particle, this little local thing that I see when the Higgs field wiggles. And the answer is yes, it has a mass. We know exactly what its value is now. It is measurable, and that particle behaves like a massive particle. So if you excite the Higgs field, when I originally made this, I had a wiggle that was moving across the screen, and I decided that was unnecessarily confusing, but it's more realistic. It doesn't just sit in one place. Just like any other particle, that wiggling spot in the Higgs field moves. And it moves slower than the speed of light. And you can push it. And you can see how hard it is to push. You can do all the things that you use to measure the mass of a particle in principle. In practice, you can't really do those experiments directly because it's gone so fast. But if we ever develop the techniques to take measurements in, those tiny, tiny, tiny fractions of a second, then the Standard Model predicts we should be able to move Higgs particles around, and they should behave exactly like ordinary particles with this certain mass. And it's huge. By particle physics standards, I mean, they're particles. They don't have the mass of a baseball or something. But it's much heavier than the vast majority of the other particles in Standard Model. Yeah?
So when the scientists made the Higgs field wiggle, did they do it in space or in particle?
They did it on Earth. So they had to bang these two protons together. And the way you do that is you have a source of protons. You know how to do that. You can strip some protons off of matter. And then you use magnetic fields to speed them up faster and faster and faster. And they move in a big tunnel in a ring. And the bigger you make that ring, the faster you can get them going. LHC is a tunnel approximately 17 miles. Now I can't remember if that's the circumference or the diameter. One or the other. Approximately 17 miles. And you actually get two of these, and you get them rotating around. They're two slightly separate rings, so they miss each other. So you get them going faster and faster around these rings, until finally you bring the two together, and you smash them into each other. And I keep talking about this discovery being in Switzerland, because the research center, CERN, is in Switzerland. But the tunnel itself is so big that it actually stretches between Switzerland and France. It is an underground tunnel that crosses the border between Switzerland and France. Yeah.
So you were saying that in theory, scientists could get the Higgs particles to move around the same as any other particle.
Right.
Currently, can the explosion of other particles that the destruction of the Higgs particle creates, does that move around in a group, or do they
yes.
become their own separate particles?
So the question was, how does the particle, after the Higgs decays and it shoots off these shower particles, how do they move? Do they move in a group, or do they spread out all separately? And the answer is some of both. They do all spread out separately, But if the Higgs particle that created them is moving this way, then they, on average, are more likely to be moving that way than that way. So you get a shower of particles going in all directions, but there'll be a few more of them heading that way, heading in the direction that the Higgs particle is moving than the other way. And if you average all of their motions, it averages out to the motion that the Higgs particle had to begin with. And for any of you who've had a semester of physics, what I mean when I say average their motions is average their momenta. For those of you who haven't had a semester of physics, don't worry about it. Yeah?
Well, I know that earlier this year, a lot of people were talking about neutrinos. Can you explain
Aha.
why that was such a big deal?
Yes. So this is the second big announcement in particle physics this year. Both coming out of CERN, by the way, because the LHC is the biggest particle accelerator out there. So interesting things tend to come from it. There's a crucial difference between the two. This one, as soon as it came out, everyone thought, yes, that must be right, because it's what we expected to happen. This earlier one, which I'll describe in a moment, as soon as it came out, everyone thought, that's going to turn out to have been wrong, because it was so different from what everyone expected. The theory of relativity predicts that nothing can move faster than the speed of light. It in fact predicts that a particle with mass should move slower than the speed of light, and a particle with zero mass should move at exactly the speed of light. And those are really the only two options. There was an experiment where they produced these kinds of particles called neutrinos. They're in the list of the standard model I showed at LHC at CERN. And they shot them hundreds, I think almost 1,000 miles, and detected them in Italy. And they very carefully measured how fast they moved. And they did it in a delightfully simple, old-fashioned way. They carefully measured the distance, and they carefully measured the time it took, and they divided. And what they found was that the neutrinos were moving faster than the speed of light. This is huge. It completely overturns our basic understanding of how particles work, except almost everyone in the physics community assumed it had to be a mistake, because it was so unexpected. Now, you never know for sure. Many of the greatest advances in science have come from things that people assumed had to be wrong because they were so much against what people already believed. So you never want to discount things like that out of hand. But it is worth also remembering that you always hear about those things, the great advances that nobody expected. What you don't hear so much about are the other 99.9% of things that nobody expected, which were in fact wrong. And it turns out this was one. They had measured the distance using GPS. The problem was, the GPS was accurate enough, but the place in Italy where they detected it was at the bottom of a mine. And the GPS receiver doesn't work at the bottom of a mine. So they used GPS to measure the distance from CERN, where these were produced, to the entrance of the mine, and then tried to really carefully measure the distance from the entrance of the mine to the detector at the bottom of the mine. And there was a faulty connection in one of their wires. And they caused them to measure the distance slightly incorrectly. And when they corrected for that, turns out neutrinos were moving slower than the speed of light. It is nonetheless a wonderful and important story, first off, because it shows the importance of being unbelievably careful with these experimental measurements. But also, it's a real example of how science works. The fact that it turned out to be wrong doesn't in any way invalidate the correct work that these scientists did in finding that result and publishing it and saying, here's something unexpected, we got to figure out, is this a real result or not? And eventually they did. But bottom line, neutrinos do still move slower than the speed of light. Yeah?
So how many times did they bang the protons together before they decided we found the Higgs boson?
Aha! So that brings up another thing that I decided to gloss over in the talk and wait and see if it came up in the questions. I mentioned that you can't see this wiggling Higgs. All you see are the particles that come out afterwards. And then you say, yeah, those are the kinds of particle showers we would expect from a Higgs. How do you know that it wasn't actually just produced directly from the protons? The protons collided together, there was no Higgs field, it just produced that shower of particles. Well, the answer is, statistically, you expect certain kinds of particle showers from direct collisions of protons, and you expect other kinds of particle showers from a decaying Higgs particle. So nobody can point to any one collision at LHC and say, that's one where a Higgs particle was created. What they can do is they can point to dozens of collisions out of the millions that they performed and say, statistically, we got so many showers that looked like Higgs and it would have been really unlikely from a direct proton-proton collision that there's no way by chance that this happened unless there's a Higgs. So it's all statistical. And to directly answer the question about the numbers, how many did they observe? Millions and millions of collisions to get a small handful that looked like the signature of a Higgs. But you can run the statistics and say, that's exactly what the standard model predicted. If the standard model is right, you should have gotten about this many showers that looked like that. And if there were no Higgs, you should have gotten a tiny fraction of them. You could have gotten one or two, but you wouldn't have gotten a dozen without the Higgs. And increasing the confidence, there are actually two completely independent experiments running at LHC. And they did this just in case there was some systematic error that caused them to see something that wasn't really there. They ran this twice in two different places, and they both got exactly matching results. The statistics exactly match in both experiments what the standard model predicts. But the number of collisions is enormous for a very small number of Higgs particles. Yeah?
Does the Higgs field expand exponentially with the universe, or is there like a set limit to how large it can be?
Okay, so the question was, does the Higgs field expand as the universe expands? And the answer is yes, but I have to be careful to be sure we're talking about the same meaning of the word expand. The Higgs field is the same now as it was a billion years ago. It's the same here as it is somewhere else, and it's the same as it will be a billion years from now. But as the universe expands, that Higgs field, which is exactly the same everywhere, is the same in a bigger region. So it fills, however big space gets, the Higgs field continues to fill that entire space in exactly the same way as it did a billion years ago. That's not, by the way, how ordinary fluids behave. If I took a balloon out in space filled with air, and then I pulled the rubber out so that the balloon became twice as big, and it was very strong rubber, so somehow it didn't pop, the air inside would be half as dense as it was before I did that. It wouldn't be the same before and after, because it would be the same amount of air filling a larger volume. The Higgs field doesn't behave that way. If the universe doubles in size, you end with the same Higgs field everywhere, and it's just filling twice as big a region as it was before. Yeah?
How does the Higgs field work with the idea that energy can turn into mass and mass can turn into energy?
Okay, the question was, how does this relate to the idea that you can turn energy into mass and mass into energy? Or I would even put that another way, that really the way we think about it now, mass is just one of the many forms of energy out there. And that is crucial to the process I showed before. The Higgs field contains energy. Especially when you wiggle the Higgs field, that contains a certain amount of energy. You take the protons that are coming in, all their mass energy gets turned into Higgs energy, which gets turned into the energy of these other particles. Excuse me. And it's all an example of this much more general process. It's not just turning energy into mass, or mass into energy. It's turning any form of energy into any other form. The theory of relativity says that mass is just one more kind of energy. And you can, in principle, turn any kind of energy into any other, as long as the total amount of energy remains the same. So before the collision, you had 2 protons. Now they're gone. And instead, the Higgs is wiggling. You've turned all the mass of those protons into energy of motion of that Higgs field. And then a fraction of a second later, that energy gets returned back to particles, but different particles, than the ones you started with. So you're converting mass to energy and different forms of mass to different forms of energy and so on, but the total amount of energy is always staying the same. Yeah? Yeah?
You said that in our entire universe, the Higgs field is completely equal.
Mm-hmm.
But the image you showed of it shows the Higgs field like a cube, where it has different values, and that's what happens when it wiggles. It's going to those values.
Ah, excellent. So let me return to that image and clarify. This is not a cube. It looks like one. But in fact, this is only a square. Because I had to use one dimension, I had to use the height to represent how big is the Higgs field at every point. So what that represents is, if you imagine, say, one of these bricks on the wall, and I ask, what's the value of the Higgs field at every spot on that brick, flat two-dimensional area? It's this high here, and this high here, and this high here, and it's the same everywhere throughout that two-dimensional region. If I come 1 foot off the wall and ask, what's the Higgs field here? It's still the same there. But I can't plot that, because I need to plot 3 dimensions for space, and I still need to somehow show what's the value of the Higgs field at every one. So this is only showing the Higgs in a flat two-dimensional region. And when it wiggles, what that says is there's some spot in the middle of the brick. It's not moving off the wall or into the wall, the way the picture makes it look. It's just that the Higgs field gets denser in the middle of the brick, and then less dense, and then denser, and then less dense, and so on. Yeah?
Do people attribute this, the Higgs field to other dimensions? Like, when we studied physics, we talked about other dimensions that might be possible. Do people have a theory of how that connects to the Higgs field?
So the question is, how does the Higgs field relate to the idea that there might be more dimensions of space? We think of ourselves as living in a 3-dimensional world. It is possible that we actually live in a 4-dimensional world, or a 5-dimensional world, or an 11-dimensional world, as string theory suggests. That may very well be true. A lot of particle physicists, for a lot of reasons that it would take me very far afield to get into, suspect it probably is true. But it actually doesn't alter the picture I'm talking about with the standard model much. What it really tremendously alters is the idea of physics beyond the standard model. All of the particles in the standard model, if that's true, seem to just move around in 3 dimensions. But it may be that there are other kinds of particles that can move in these other dimensions. And one way you might see that, so imagine a 2-dimensional being who lives only on this wall. And that being does not know that there is such a thing as the 3rd dimension. It does not know that this room exists, and if you told it this room exists and it asked you, well, where is it? There is no answer you could give it that would make sense. Is it north, south, east, west? No, it's a different direction. Same thing, if we live in a 4-dimensional world, or more, it's not that way, or that way, or that way. It's a different direction that I can't move in, and I can't even look in. But maybe there are some kinds of particles that can. That is one of the things people are looking for at LHC. There would be an exciting window into new physics, and the way you would see it is if you smash some protons together and a bunch of particles come flying out and you carefully count up all of the energy in all of the particles you produced, and it's less than what the protons had to begin with. That means something somewhere went missing. Well, there are a lot of ways that could happen, but one possibility, if that happens, is that you created a particle that moved off of our dimension. And again, you can picture that by thinking of this two-dimensional being. They were in their own two-dimensional particle accelerator, and they smashed two things together, and they see 7 particles come out, but unbeknownst to them, there's an 8th particle that came out this way. From their point of view, some of the energy in that collision just disappeared. And so that's one thing that people are looking for at LHC, is signatures of missing energy. Problem is, if you find missing energy, maybe it means there's an extra dimension, or maybe it just means there's some kind of particle that your detectors can't see. It's very hard to disentangle those two, but it's a hint. And people are actively looking for it. So far, no evidence has been reported of that.
I think we need to stop here, just because eventually these girls have to eat dinner. So Gail.
I just want to say thank you, Professor Felder, for giving
Great pleasure.